All right, good afternoon, everyone, and welcome to this Department of Energy Basic Energy Sciences User Facility Science webinar entitled Forefront Microelectronics Fabrication and Characterization. We have four very interesting and I hope exciting talks today from people working across the DOE Basic Energy Sciences User Facility Complex. My name is Andy Schwartz. I am the Division Director for Material Sciences and Engineering within the Office of Basic Energy Sciences at the Department of Energy, and I will be moderating this webinar. We're going to start with a very brief introductory overview of the DOE Basic Energy Sciences facilities from my colleague, Dr. Dava Kivney, Program Manager in Basic Energy Sciences. So I turn it over now to Dava.
Hey, thank you, Andy. Yes, I'll just introduce myself. My name is Dava Kivney. I'm the Program Manager in the Scientific User Facilities Division within Basic Energy Sciences, and I cover X-ray light sources primarily, and also nano science research centers and neutron sources. So if we can go to the next slide, I'm going to give a little overview of BES and our facilities and kind of what they can do, and in case folks there are folks in the audience who are not familiar with our facilities. So Basic Energy Sciences is focused on the understanding of basic properties of matter and energy across many length and time scales. So we support basic research into like materials, discovery, chemical processes, and applications important for energy. That includes phase formation, catalysis, magnetism, electronic structure, and dynamics, and much more. We do this through a broad research portfolio, which includes our core programs and cross-cutting activities like energy research, energy frontier research centers, and also operating 12 world-class scientific user facilities comprised of X-ray light sources, neutron sources, and nanoscale science research centers. And we are also constantly upgrading these facilities to maintain them as world-leading resources. We can go to the next slide. So this is just a map of where they are. We have 5 X-ray light sources, 5 nanoscale science research centers, and 2 neutron sources, and they're scattered around the country at our national labs. If we can go to the next slide, I will give a little bit of overview of how these places work. So our X-ray light sources are particle accelerators that make use of the fact that when the general property that when you bend a charged particle beam, you get light emitted. And for a synchrotron, which is a circular accelerator, electrons are orbiting in a ring-shaped path, steered by magnets, and they're passed through devices called either wigglers or undulators that force the beam into a oscillating path using rows of opposing magnets. At each of these oscillations, you get X-rays out, depending on the energy of the beam and the period of that oscillation and everything. There can be dozens of these repeats, and so these add up to create very bright, focused beams, which are then collected using specialized optics and focused into an experiment station for a given experiment. There's also a linear accelerator sort of variation on this, where you feed the beam from a very long linear accelerator into a very long undulator, and that creates an X-ray laser. Typically, a synchrotron is about 1 billion times brighter than a medical X-ray, and an X-ray laser can be another 1,000 times brighter than that. And a synchrotron can feed dozens of beamlines at once, and all doing independent, different experiments. So it's a very broad base of type of facility. The X-ray laser the beams can also be multiplexed to serve more than one user at a time. Not as many as a synchrotron, but more than one at a time. If we can, okay. Oh, and let me go to the next. So the nanoscale research centers these are focused on providing instrumentation and equipment for the synthesis, fabrication, and characterization of materials at the nanoscale. They offer tools for deposition, processing, lithography, imaging, and they're usually co-located with one of our light or neutron sources to enable complementary capabilities to work together. And in fact, they often have co-run beamlines at some of the Xray facilities, for example. And then the two neutron scattering facilities, which are both at Oak Ridge National Lab. We have a reactor source, the high flux isotope reactor, and the spallation neutron source. And these offer multiple neutron beamlines each for basic research in materials and processes for energy. We've been running these facilities for many years, but we are not standing still. Many of these facilities are undergoing major upgrades right now to help keep them at the forefront and deliver the needed capabilities that are going to come into play for microelectronics, materials discovery, and device characterization. On the immediate horizon, for example, the advanced photon source at Argonne National Lab is currently replacing its entire wing with a new design, which will improve the brightness by 500 times. And our free electron laser, which is the LINAC coherent light source at Stanford Lab, is on the verge of opening up a new LINAC that will improve its average brightness by 10,000 times. So, and our nanoscience research centers are undergoing a recapitalization project to improve and update and expand their instrumentation as well. So, if we can go to the next slide. Yeah, this is just a sort of give you an idea of the scale of some of these facilities. These are very large scale facilities. A synchrotron can be hundreds of meters in circumference. The largest one we have is 1,100 meters, or they can range to lab size instruments like electron microscopy and that sort of thing, or deposition equipment. If we can go to the next slide. And we've had this is just a few examples of some of the scientific impact that our facilities have had. I won't go through all of these, but yeah, you can also find many more of these on our website, the BES website, and also on the facilities websites. If we go to the next slide. And so our user facilities serve over 15,000 users each year from all over the place, all over the globe. Access to these facilities is free, minus with exceptions for special materials and that might need to be bought. But it's basically free for access for non-proprietary research. And it's awarded through a competitive proposal review system, which these are managed by the facilities themselves. So rather than going to giving all the links, here's one link where you can get to all the facilities. And this is on the EUV Office of Science website. And so with that, I'm going to turn it over back to Andy. And this is the collection of talks that we have. We're going to hear about new materials discovery, new devices, pushing the edge of lithography, processing for energy efficient microelectronics and new discoveries, new materials discoveries as well, and also forefront imaging, 3D imaging of non-destructive imaging of integrated circuits. So with that, I'll turn it back over to Andy for the.
Great. Thank you, Dava. Appreciate that overview. One or two very brief comments about the format of the webinar and a little bit of housekeeping. So as Dava just said and showed you here, we're going to have 4 talks. They're each intended to be approximately 15 minutes long, and that will leave us about 20 or 25 minutes for Q&A at the end. So we'll take questions from the audience at the end of all of the 4 talks. However, if you notice, the questions will be done through the Zoom Q&A, which should be at the bottom of your Zoom window. If you click on that, you can enter questions at any time. You can enter them during or after the individual talks. We'll try to get through as many as we can live at the end, though we also may be able to answer some questions through the Q&A as well. So again, if you're interested in posing questions to the speakers individually or collectively, please enter those into the Q&A. Okay, our first talk is going to be entitled Polymer Semiconductors and Electronics, Empowering Innovation Through Autonomous Discovery. And the speaker will be Dr. Jay Xu from the Center for Nanoscale Materials at Argonne National Lab. This is one of the 5 nanocenters that Dava spoke about before. So I turn it over to Jay for her talk.
Thank you, Andy. Thank you for the great introduction. So today I will talk about an exciting journey into the future of technology. So we will explore the world of polymer electronics, materials that can be as soft as our skin and even degradable, biodegradable. I will also share with you the power of the cutting-edge self-driving lab at CNM we recently developed at the Argonne National Lab. This is a new research approach that we believe can accelerate the discovery and bring those polymer electronics to our daily life sooner. Next slide. So so we know like today, electronics are everywhere in our daily life. We are surrounded by a wealth of information made possible by advanced electronic technologies. But imagine a world beyond our smartphones, VRs. Next slide. So where the electronics and materials can do so much more. So can we envision a future where electronics become an extension of ourselves? A world where they become more than just hard pieces, but seamless parts enhancing our everyday experience, like this soft wearables, medical devices, like soft robotics, right? Beyond just our devices, can we also consider to make device for our plants, like to help the growth and monitor and understand? And how can we make these electronics more sustainable, greener, and better for our planet? So polymer electronics holds the promise for these new possibilities and also applications as well. Next slide. So as a material scientist, my mission is to construct electronics from the very molecules that form them. However, we need to think about how to come up with materials that are soft as, like rubber here, or as soft as our skin, but have the electronic properties as good as those used in our devices. Next. So when we look into the molecular level, we face a contrast here, actually. We face a contrast between the design requirements of electronic molecules and those of rubber band type materials. They are opposite. It's like trying to balance rigid structures for efficient conductivity on one hand, while on the other hand, we need extreme flexibility resembling those rubber-like materials. So we definitely need a creative method. Next slide. So in our research journey, we seek help from something fascinating. I'm fascinated about the world of nanoscience. I'm working in a nano center. This is why I'm here. So we know that the things behave differently when we make them to the ultra small scale. The physical properties of materials can change dramatically in this tiny world. So in our case, we discovered that the nanoscience here, more specifically nano-confinement, gave us a way to make our target material. So here we found that by making those conjugated polymers, a class of polymer that show unique optoelectronic properties. So into those kind of nanoscale structures, they can not only transport electronic charge carriers more efficiently, but also gain very good mechanical stretchability or ductility. So now we have the stretchable, soft, semiconducting materials. So here, the video just played is a real-time video of an operating stretchable transistor made by this stretchable semiconducting materials. So when we stretch it, twist it, or even here, poke on the sharp object, so the transistor behave almost the same. So this is pretty good. So the material innovation is important for us to be able to make different new type of electronics. Next slide. I'll show you some example. So we can make a skin-like sensor arrays and place it conformably on our hand to sense the object. For example, here we can sense the location of an artificial ladybugs. Or we can use the degradable light-emitting polymer we developed to build a greener displays. So this is pretty exciting. So But I would like to say this is just the beginning. So next slide, I'll give you the brief timeline. Right? This is the evolution of flexible electronics also the evolution is remarkable as shown in this brief timeline. However, let's see, it's pretty long time, right? It takes us pretty long time to where we are. Then to truly empower the innovation and bring those polymer electronics to our daily life sooner, we require accelerated discovery methods. The reason is pretty easy. Next slide. So yeah, like this is because like developing polymer electronics, it actually involves exploring an extensive design space, like from optimizing single chain polymer chain structure to their assembled morphologies and all the way to the fabricated multi-layer device structures. So the total design is very complicated. And I think this is pretty common for a lot of research as well. Next slide. I'll share an example from my own research to highlight the need for a new research method. So for this research, the goal is pretty simple. So we want to solution print a stretchable semiconducting polymer with improved electronic property. So you see here, we spend a month to design what are the strategy we're going to use to enable our goal. Then we spend 2 months to synthesize all the materials required for this study. Then we spend 10 months to do the repeated device fabrication data analysis to do the optimization. Then once we have the optimized device, which we think that's optimized, but that might not be true, then we use this condition to fabricate a device. So I think this is probably similar to some of your research as well. We want a new method to help us to minimize the time here, especially in the optimization period. Next slide. So then over the time, then we look back. So over the time, we find the tools for discovery actually have evolved and transformed. And our journey of exploration has been shaped by the tools we used. So today we stand at the forefront of autonomous age. So this age is armed with powerful computers, AI algorithms, and advanced automation technology. We definitely can do something different for our research. Next slide. So let's just imagine. So let's imagine a situation where, given a problem, a lab computer automatically chooses what experiment to do based on its database. Then a robot carries out this experiment, tracks the result with integrated sensors, then analyzes the results and decides what experiment to do next until it finds the solution, then suggests it to us, to the human researcher. So the concept is great, right? So we can use a robot to do the research. Then how is the robot works now? Next slide. So let's see. So actually in today's world, the industry has utilized—
Hungary, producing 2 million engines.
Yeah, in the industry, actually, industry has utilized robot to build cars with precision and efficiency. However, when it comes to research, the landscape changes, right? Research, we are seeking for originality. We're seeking for discovery, while robotic manufacturing is aiming for the same result. So, but what if we could bridge this gap? What if we could develop intelligent robots capable of inventing and making new molecules on their own? Well, the answer is, why not? Next slide. So over the past 5 years, my group and also my colleagues, we have been working together to develop, on a very exciting journey. We have been developing an AI-driven robotic laboratory at the Center for Nanoscale Materials at Argonne. We name it Polybot, also known as our self-driving lab. So what sets Polybot apart is its seamless integration of automated synthesis, processing, characterization, and the mobile robot. Everything is driven by advanced AI algorithms. And furthermore, in collaboration with scientists from the data science division at Argonne, we have developed a web application that facilitates the integration of different platforms across different facilities, such as from our APS, Advanced Photon Source, and also from our supercomputer at Argonne National Lab. So this kind of allows us to gain in-depth characterization. It is also allow us to do more complicated computational work. So this is where we are. This is what the self-driving lab looks like now at CNM. So in the following part, I will give some example I'll show you some examples of the electronic materials and the polymer devices that we are exploring with the Polybot. Next. So the first example I would like to show is the controlled assembly. So we know the controlled assembly of electronic materials, especially electronic polymers, has been crucial in the electronic and energy industry. However, it remains a challenge to do the high throughput producing of electronic polymer thin film with desired properties. So for this study, we want to print a conductive polymer thin film with high conductivity and also uniformity. But there are actually 8 formulation and processing parameters that we hypothesize will influence the properties. And the entire exploration space is actually over 500,000. This will take decades, or probably impossible for like student or researcher to screen all. Now in our self-driving lab Polybot, we integrate Bayesian optimization and Gaussian process regression machine learning algorithm to this robotic workflow that you are currently seeing here in the video to quickly analyze the relative importance of each parameter and quickly identify the path to the desired property. Robot carries out everything autonomously. So here, instead of performing 500,000 experiments, Polybot found our target conductive films within 100 trials. This is pretty exciting. This is actually our first demo from Polybot. Next slide. So this research is about autonomously design the chemical structure of electrochromic polymers and synthesize them automatically with full color optical properties and ability to modulate like optical transmission reversibly on the applied potentials. So the video actually shows that our synthesis robot is selecting building blocks recommended by our machine learning model and autonomously cooking the polymer. Once the polymer gets synthesized, a mobile robot seamlessly transfers the sample for property evaluation. The entire process is driven by like robot and also machine learning. So this is a new, I would say a pretty good platform for polymer electronic applications. And the material we develop here can be used for smart windows, displays, and other optical devices. Next. So this is the last example I would like to show. So in this research, next slide, please. Yeah, so in this research, Polybot actually goes beyond just producing material, but automating the fabrication of devices and enabling the direct study of materials property within the fabricated devices. So we know that electronics material is important, but evaluating the material in real device is also important. This is all about this research. So the device that Polybot is making in the video is the organic electrochemical transistor, OECT, which can serve as a universal like biosensing platform with high amplification, and also a building device for neuromorphic computing. So you see here the way like Polybot seamlessly combines device fabrication and material analysis makes it suitable for different electronic research areas. I hope now these 3 examples can give you a brief idea about the capability of Polybot for the polymer electronics. Next. So as I conclude my talk, I invite us all to think a question. How much can we accelerate the advancement of new capabilities for future polymer electronics through AI and robot, and integrate the polymer electronics into our smart society? So this is an open question. I'm working on it. I'm looking for the answer. Next. So lastly, I would like to thank the great Polybot team. It is through our cross-disciplinary teamwork that we stand where we are today, and of course, with endless possibilities still ahead of us. Polybot is now available as a user tool for everyone at the Center of Nanoscale Materials at Argonne, and we extend a warm invitation to all of you to use it for your own research. Thank you so much for your attention.
Thank you very much, Jay. Appreciate that. Wonderful talk. Again, for those who joined later, just as a reminder, if you have questions for Jay or any of our other speakers, please enter them into the Q&A box in Zoom, which you should find at the bottom of your Zoom screen. And we'll answer questions and have discussion at the end. So moving to our second talk, it is entitled EUV Lithography, Pushing Chip Manufacturing to the Extreme. Speaker is Dr. Patrick Naulleau from Lawrence Berkeley National Lab, where he has been involved as the director of the Center for X-ray Optics for a number of years. Turn it over to you, Patrick.
All right, thank you, Andy, and welcome everybody. So today I hope to give you a story, a success story in terms of how research at the national labs and the synchrotron facilities in particular over the past few decades has actually led to transformative impacts on all our lives through EUV lithography. So on the next slide, as you all already know, right, advanced computing is critical in nearly every aspect of our lives. And we just heard an example on in the previous talk, which was quite inspiring, right, in terms of, for example, science and engineering. It's now impossible to make significant progress in those spheres without advanced computing. It's also obviously used in health, automotive, and transport, right? Think back at COVID. We couldn't get cars because we couldn't get chips. It's not that we couldn't make the physical car. We couldn't get the computer chips to drive the cars. Internet and telecom, same thing there. That one's the obvious case. But also in terms of our clean energy and sustainable energy future, advanced computing is critical to any future there. So how has all this been possible? In the future, in the next slide, you'll see that all this advance in computing has been enabled by advances in semiconductor processing. And this advance has been captured by something called Moore's Law. It's actually more of an empirical law, and it was first described in, believe it or not, 1965 by Gordon Moore, who at the time looked at some empirical data and said, look, the number of transistors that we can get per chip is doubling every 2 years. And he projected that that would keep going on into the future. I don't think even he believed that it would keep going for 50 years, but it's still going on today. And this improvement is what's driven the improvement in advanced computing. Unfortunately, we lost Gordon Moore just this March, but he's had tremendous impact on this industry. He was one of the founders of Intel. So yeah, on the next slide, this is, those graphs are nice, but to really understand the impact of what this means, right? Doubling every 2 years, that's incredible growth. And I like to use this example, and I teach my EUV class. If you look at Amazon today, you can probably buy this 200 gigabyte chip. That's about the size of a fingernail, and it costs about $25. If you think back of what this amount of memory would have cost in 1970, it's kind of staggering. And that number is $400 billion. Now, obviously, we couldn't even have made this much memory back in 1970, but this is, in a nutshell, the power of Moore's Law. But Moore's Law, as you will see on the next slide, is not just about making things cheaper. It's in fact also about making things more energy efficient. So in parallel with Moore's law, there's another law that we refer to as Cumis Law, and it says that energy efficiency actually of computing devices doubles every 18 months. So energy efficiency is actually improving faster than the density of chips. And that's been critical because it means that we can get all this additional computing power without consuming 100% of the world's energy. So this has allowed us to get more and more power. And you can see that Moore's law is continuing on into the future, as we will see on the next slide. Here, often we've heard about Moore's law coming potentially to an end, but we're now sitting in roughly in 2022 in what's called the 3 nanometer node. Even though it's called the 3 nanometer node, in fact, the structures we make on the computer chips that you're going to see actually in exquisite details in the final talk today, those structures are only 22 nanometer lines that are separated by 22 nanometers. So the naming convention is a little funny in terms of what we call 3 nanometer node, but that means that we still have a lot of room to push things further. In fact, we predict about another decade and a half, we can keep scaling things with Moore's law down to line separations of about 12 nanometers, where we'll start also integrating 3-dimensional structures, as you'll hear in the next talk. So on the next slide, you can see how we've done this scaling. So when you write computer chips, we basically are doing printing with light, and how small of a feature you can print in the computer chip is proportional to the wavelength of light that you use. So back in the 1970s, we were using white light, and then in the 80s, we switched over to blue light, and then in the 90s, ultraviolet light, and finally in the 2000s, we went to deep ultraviolet light, but then we kind of got stuck there, and that's in the 248 to 193 nanometer range, and we got stuck there because we were unable to make glass that was suitably transparent to push the wavelength even further. So we pushed the deep UV technology as long as we could, and then needed to jump to extreme ultraviolet lithography, and that's at 13.5 nanometer wavelength. And in that case, we could do it because instead of using glass, we used mirrors to reflect the light instead of traditional lenses. Again, EUV light uses only 13.5 nanometers in wavelength, which means you can print extremely small features. So on the next slide, I'll give you just a quick overview of what EUV lithography is, and in fact, what any lithography is. So you start with a light bulb, and in this case, it's going to be an EUV light bulb. We shine it on what we call a mask, which is the master of the circuit pattern that you are looking to replicate into a computer chip. And then you've got a lens or a mirror-based system that takes a picture of that master pattern, shrinks it down, and projects it onto a silicon wafer. And then the silicon wafer is coated with a chemical film, much like old school film cameras, where you had this chemical on your plastic film, and that recorded the image. In this case, we record the image on this film on the silicon wafer, and then we use etch machines to etch that picture into the silicon wafer and make a working electronic circuit. So you can see in this process of lithography, which is just, you can think of it as photography or a photocopier process, the resolution equation is K1 lambda over NA. K1 and NA are nominally fixed physical constants, and lambda is the only thing that we can continuously shrink. So lambda is the wavelength of light that we use, and that's why over the decades, we've pushed to shorter and shorter wavelengths, and now ultimately EUV or 13.5 nanometer wavelength. Now, to do this work early on, all right, where could you get this 13.5 nanometer light? Well, one of the major challenges in developing EUV lithography was, in fact, making the light bulb. And at Berkeley Lab, we had access to a synchrotron, right, the Advanced Light Source Synchrotron facility, which was one of the world's brightest sources of EUV light. So in parallel with the community developing these new light sources, these new light bulbs that could be used in manufacturing, we had the ability to use a light source that we already had sitting there to learn everything else about the process. For example, issues around the mask, the optics, and that film that we have to put onto the wafer. So on the next slide, you can see the beam lines that we started putting together. The program, in fact, started at the ALS in 1994, and we built 3 of the first generation research beam lines focused on addressing all the questions about EUV other than the light source itself. So one of the key ones was learning about these EUV optics. How could we make mirrors that were suitably reflective in the EUV regime? It turns out to be very complicated, and you need nano-layered structures to do it. Another major question was the mask. Imagine that the mask is the master for every computer chip that you make. If you have a single imperfection on that mask, every single chip that you make will be defective. So you can't tolerate any defects at all. So we needed to learn about what causes defects, what do they look like, how can we prevent them. But we built a microscope at the synchrotron to do that. And finally, we needed to learn about the entire process of projecting this image onto the silicon wafer, recording that image into the film. So we developed another beamline end station specifically to prototype the entire lithography process. So with all this work was going on for about 25 years. And finally, as we'll show on the next slide, that EUV was brought to commercial reality in 2019. And the very first chip was the one shown here on this picture. And if any of you had a Samsung Note 10 at the time, that would have been the first commercial device fabricated with EUV lithography. Now, the very next year, Apple also turned to EUV lithography for all their chips as well. So now any modern cell phones you get today are made with this technology. Any modern computers, all the NVIDIA chips, all the leading edge computer chips made in the world now are done with EUV lithography. So it sounds like the job is done, but in fact, we're just at the beginning. And we spent decades and billions, or actually tens of billions of dollars to develop this technology. So we need EUV lithography to keep going into the future. So what are the next challenges? And we'll show you on the next slide, is to keep moving EUV lithography forward. We're actually now constrained no longer by the optics and the light bulb and all these things that we studied for the past 3 decades, but we're really more constrained by the fundamental materials challenges in making things even smaller. So today with EUV, we print things that are about 22 nanometers in spacing, where we need to get to enable the next decade and a half of technology is to go to something like 6 nanometer lines and spaces, or 12 nanometer separation of the lines. So we need fundamentally new materials to make this happen. And that's both on the mask as well as on the wafer, where we have this film that needs to record this image. And we're going to need to now record this image at fidelities that are nearly at the atomic level. So to address these questions, we've now started developing a new set of beamlines at the ALS, as shown on the next slide. And these are focused really on fundamental materials characterization. So on the mask, instead of just using the mask to absorb or let the light transmit, we're now going to use the mask to actually control the time delay of the light. And doing that, you can get additional imaging capabilities from your lithography system. So that is a new challenge that's coming forward that we need to be able to address to push lithography or EUV lithography forward. Also, I mentioned we need to control these films at the nanoscale. So how do we do that? Normally, the only thing we have access to is the image after we've recorded it in the film and transferred it to the silicon. But we really need to understand what's happening in that film itself. And to do that, we need to be able to visualize the chemistry in the film after we've patterned the structure in there. So we need to do very, very high resolution 3D imaging of the chemistry inside the film itself. And to do that, we're using a technique called RSOC, so resonant soft X-ray scattering. So there's a new beamline that's been developed for that. And another unique thing about EUV lithography materials, even though EUV light goes into the film to record the image, it's not the EUV photons that do the work. The EUV photons generate some photo electrons, and it's in fact those electrons that ultimately do the work. So in order to understand the fundamentals of the process, we also need to understand the fundamentals of these electrons that are generated, how those electrons move, what chemistry those electrons do. So we've developed another suite of instruments at the synchrotron that is dedicated to these electron studies. And all these experiments are really focused on extremely high resolution, learning things at the nanoscale, and the next generation upgrades that you heard about in terms of these light sources, the ALS-U upgrade that will be coming that will make the light source, say, 1,000 times brighter, that will significantly enhance our abilities to do these measurements, these types of measurements and learning as well. All right, so that takes me to my conclusion. And hopefully, I've convince you that EUV lithography has been critical to the continuation of Moore's law and exponential scaling of compute power. This really has been enabled by research at the ALS over the past 25 years, and we're continuing to enable this technology for the next decade and a half to 2 decades with new research at the ALS. And that is because what's constraining things now in terms of the future of EUV is really fundamental materials challenges, which is right in the wheelhouse of what the Department of Energy has their expertise in. We believe that EUV and soft X-ray techniques developed at the ALS will continue to play a crucial role in overcoming these challenges and enabling the future for all of us. So with that, I thank you for your attention.
Wonderful. Thank you, Patrick, for that. Really appreciate that talk. Okay, moving on to our third talk. The title is X-ray Visualization of Semiconductor Processing for Energy Efficient Microelectronics. We heard a preview of efficiency in Patrick's talk, so that's a good segue. The speaker here is Dr. John Baneshki from the SLAC National Accelerator Lab, and I turn it over to you, John.
Okay, thank you for that introduction. Next slide, please. First, I will discuss microelectronics and driving forces for more energy efficient computing, and then introduce embedded non-volatile ferroelectric memories as a potential pathway for more energy efficient computing platforms. Subsequently, I'll highlight capabilities at SLAC for X-ray visualization of semiconductor thermal processing, and then conclude with a summary. Next slide, please. Advancements in microelectronics underpins all aspects of modern society and is critical for basic science research. As we have heard from previous speakers, we're all aware of the impact that microelectronic devices such as personal computers, smartphones, and smartwatches have had on our daily lives. In basic science, advancements in microelectronics are critical for energy efficient high-performance computing, as well as the development of specialized technologies for extreme conditions such as high radiation environments or cryogenic temperatures. 2 examples are shown on the left-hand side and include application-specific circuits, or ASICs, for an X-ray camera, for the LINAC coherent light source, or LCLS, X-ray laser, and a readout system on chip for the next enriched Xenon observatory, or NEXO experiment, to detect neutrinoless double beta decay of Xenon 136. Both are designed by SLAC. There are increasing demands for microelectronics to enable energy-efficient edge computing for real-time data analysis to handle the vast streams of DOE light source data projected to reach 700 petabytes by 2028. Next slide, please. In addition to device scaling challenges to continue Moore's law, energy consumption is becoming a critical factor for microelectronic computing systems. New application spaces such as AI have been accelerating energy use since 2010 and computing energy use is now doubling every 3 years or less. This is demonstrated by the figure on the right, which plots the compute energy in joules per year versus the year. The compute energy is increasing with the number of zips or zeta instructions per second, and the current trend of reduction in switching energy per bit at the transistor level is not sufficient to slow this trend. Other microelectronics energy use, such as communication, electrification for decarbonization, are also accelerating. By the year 2030, computing usage is expected to be 21% of global electrical energy demand, leading to a market's dynamic limited scenario, as energy is needed to power other societal infrastructure. This will restrict the impact of microelectronics on society with serious consequences for national security and scientific advancements. Innovations across the computing stack, from new materials and devices to circuits, architectures, and algorithms, will be needed to circumvent this pending energy crisis in computing. Next slide, please. The figure on the left shows energy per operation in joules for transistors, AI, ML accelerators, and the top 500 supercomputers from 2008 to present day. The energy per operation spans almost 10 orders of magnitude. At the transistor level, the energy per operation for state-of-the-art CMOS nodes is on the order of 10 atttajoules per attajoules, where an attajoule is 10 to the minus 18 joules per bit, while the energy per operation for AI ML accelerators is 5 to 7 orders of magnitude larger. This dramatic increase in energy per operation is due to a variety of factors. One important component is data transfer. Present computing systems which employ the von Neumann architecture have data shuttled via a controller between compute and off-chip high-density memory. With on-chip memory limited by large SRAM size, there is an extraordinary volume of data traffic between processor and off-chip memory that adds to energy consumption and latency. Thus, there is a need to decrease memory latency and energy penalty associated with data transfer. As will be discussed, a promising approach is 3D integration. While the switching energy at the transistor level is in the attajoule range, the energy consumption of volatile static random access memory and dynamic random access memory are significantly higher due to the standby power that due to the high standby power for SRAM and a high write energy for DRAM, as well as the need to constantly refresh the memory content of DRAM. There is also a need for ultra low power dense and fast non-volatile memory to enable more energy efficient computing systems. Next, please. One approach to bring compute and memory closer together is 3D monolithic integration, where non-volatile memory is integrated into the back end of line. The figure on the left shows a scanning electron microscopy image of a monolithically integrated stack at the 130 nanometer CMOS technology node. At the bottom of the stack are the transistors fabricated in the front end of line, and above the transistors are alternating layers of metallization and dielectrics that connect the transistors to form logic circuits, as well as connect the chip to the outside for power and data transfer. The front end of line transistors undergo high temperature processing steps, while the steps in the back end of line are limited to less than 400 degrees C for conventional thermal processing by rapid thermal annealing. A promising non-volatile memory is a ferroelectric field effect transistor, or FEFET. In this device, a ferroelectric material is used as the gate dielectric, resulting in modulation of the magnitude of the drain current depending upon the direction of polarization. For example, as shown by the figure on the upper right, when the polarization is pointing downwards, the drain current is enhanced, while when the polarization is pointing upwards, the current is suppressed. This device offers two non-volatile memory states associated with a difference in drain current. The polarization direction can be reversed by applying an opposite voltage polarities to the gate electrode. A ferroelectric material that is of intensive interest for FEFETs is hafnia zirconia alloys, or HZO, which have the fluorite crystal structure as shown in the bottom two figures. Next slide. Advantages of HZO FEFETs are non-volatility and deep scalability to sub-3 nanometer thicknesses. FEFETs have already been demonstrated at the 22 nanometer CMOS technology node and show significant promise for integration into more advanced CMOS technology nodes. They also offer nanosecond switching, low energy switching on the order of 1 to 10 femtojoules per bit, and compatibility with CMOS processes. Moreover, HZO can be grown by atomic layer deposition. Challenges include the HZO ferroelectric phase, which is metastable orthorhombic phase, and there are numerous competing structural phases with ground state energy separated by only tens of MeV. The phase transformation pathway is also not well understood. For example, as highlighted by the figure on the right, one proposed pathway involves the nucleation and crystallization at high temperature of a non-ferroelectric tetragonal phase, and then the nucleation of a ferroelectric orthorhombic phase as the sample cools. Reliability, which can be impacted by the volume fraction of structural phases present, is also an unresolved issue. Finally, for back end of line integration, high performance devices must be achieved under strict thermal budget requirements. Next slide, please. Phase transformation pathways of hafnia thin films have been studied using a custom-built in-situ rapid thermal annealing chamber at SSRL. As shown by the figure on the left, the chamber contains halogen lamps for heating of the sample and entrance and exit slits to enable grazing incidence X-ray diffraction. In this study, the phase transformation pathway of 7 nanometer thick hafnia films sandwiched between 5 nanometer thick titanium nitride electrodes was studied as a function of the temperature ramp rate. The two figures on the upper right show waterfall plots representing the diffracted intensity as a function of time and reciprocal lattice vector denoted by Q in the images. The rapid thermal annealing initiates at 0 seconds at the top of the waterfall plots. For both ramp rates, as highlighted by the black arrows, the samples crystallize to a structural phase at high temperature with a reciprocal lattice vector that is consistent with an orthorhombic 111 or tetragonal 101 phase. At the maximum temperature of 700 degrees C during the ramp, this is likely to be the non-ferroelectric tetragonal phase, as the Curie temperature is on the order of 450 degrees C for hafnium. For the slow ramp rate of 10 degrees C per second, a transformation to a monoclinic phase is observed, while the faster ramp rate of 66 degrees C per second, the final phase has a mixed volume fraction of monoclinic and orthorhombic phases. The monoclinic phase is undesirable for ferroelectric applications as the centrosymmetric structure cannot support ferroelectric polarization. Here, in situ synchrotron grazing X-ray diffraction has revealed the phase transformation pathway may depend on the heating and cooling rates, which is important information for thermal processing of these materials. Next slide, please. While RTA is commonly used for thermal processing in microelectronics, its application to crystallize ferroelectric materials in the back end of line may be problematic as the entire semiconductor stack is heated during RTA. Xenon flash lamp thermal processing is a method that has orders of magnitude faster heating and cooling rates due to intense millisecond to sub-millisecond pulsed light that is emitted from a xenon lamp gas discharge. This allows ultra-fast thermal treatments, 4 orders of magnitude faster than RTA, and potentially a temperature transient, more localized upper layers in the stack. Unlike RTA, the heating depends upon the optical and thermal properties of the materials within the stack. A schematic of a xenon flash lamp tool is given on the upper right, which shows xenon flash lamps, a back reflector, quartz window, sample stage, and halogen lamps for preheating. In addition to these potential benefits, flash lamp annealing is also a more energy efficient thermal processing method than rapid thermal annealing. Next slide, please. In a project funded by DOE, ERE, AMO, now AMMTO, AMTO, SLAC has designed and customized flash lamp annealing tool at SSRL. The image on the left shows a photo of the tool, which was co-designed with Pulse Forge. The upper part of the tool contains the xenon flash lamp housing, while the lower part contains the flash lamp chamber with a reflective cone and a sample stage designed by SLAC. A schematic image of the reflective cone, which concentrates light onto the sample, as well as sample mover and quartz sample holder, is shown on the right. The sample stage also includes a halogen lamp for preheating. Exit and entrance slit slots for X-rays are also machined into the chamber. Next slide, please. This tool was commissioned at Beamline 17.2 at SSRL. This is a high brightness and vacuum undulator beamline, enabling grazing incidence X-ray diffraction and time-resolved pump probe studies on ultra-thin films. For pump probe studies, thousands of diffraction patterns during a flash time temperature sequence are collected, enabling visualization of structural transformations in real time. For these studies, we have used tinitride and HCO tinitride stacks on fused silica with the thin film layers each 10 nanometers thick. For pump probe studies of these stacks, we have performed characterization of an ensemble of samples cleaned for the same wafer and vary the time between the flash pump and the X-ray probe. The data is then aggregated to produce time-resolved plots. Next slide, please. The figure on the left shows grazing incidence X-ray diffraction patterns of tinitride HCO tinitride fused silica stacks for a 5 millisecond flash pulse at different flash voltages. The plot presents intensity in arbitrary units versus reciprocal lattice vector in reciprocal angstroms. It's clear from the changes in the diffraction patterns that the flash annealing parameters alter the structure. In particular, we observe the increase in the peak near 2.2 inverse angstroms with increasing voltage, which is attributed to the orthorhombic 111 or tetragonal 101 phase. As a ferroelectric polarization also increases with the flash voltage, the films contain a finite volume of orthorhombic phase. The center panel shows diffraction patterns acquired from a lab source, copper K alpha X-ray, with the red trace having the same flash annealing conditions of 5 milliseconds to 700 volts in both figures. Compared to the data acquired using synchrotron radiation on the left, the intensity of the diffraction peaks are very low and preclude a meaningful analysis of the data. The high brightness of the synchrotron radiation enables structural studies to be performed on these stacks with ultra-thin layers. Next slide, please. Using Xenon pump X-ray probe measurements, we have characterized the kinetics of structural transformation. The figure on the left presents a waterfall plot of the diffracted intensity as a function of time and reciprocal lattice vector. The flash initiates at 0 seconds near the bottom of the waterfall plot. After the flash, we see the appearance of a peak with reciprocal lattice vector consistent with an orthorhombic 111 or tetragonal 101 phase. This peak grows in intensity with time. The figure on the right presents time-resolved diffraction patterns for the orthorhombic 111 or tetragonal 101 peak from 0 to 147 milliseconds. We see the emergence of two timescales. The first, the peak shifts to higher Q rapidly within 15 milliseconds with no change in intensity, followed by a growth of intensity of the peak. The rapid shift to higher reciprocal lattice vector is due to lattice contraction due to cooling. As for this process condition, the sample rapidly cools from above 1000 degrees C to approximately 500 degrees C in this time interval. At longer times, reduction in thermal diffuse scattering and morphological changes contribute to the intensity increase as the sample cools. In contrast to structural transformation pathway observed for the in situ RTA films, no monoclinic phase is observed, which is attributed partly to the rapid heating cooling rates of FLA. Thus, flash lamp annealing offers a processing route that potentially avoids formation of this undesirable phase. Next slide, please. Flash lamp annealing results in a large processing manifold, including flash parameters such as pulse voltage, pulse width, repetition rate, pulse number, and also our tool is able to have unique processing modes such as micropulsing. Traditional approaches to process optimization take a trial and error approach to finding the optimal process condition. This is not only time consuming, but may result in finding only local maxima to the performance metric that is desired to be optimized. To open up the black box and explore process property relationships more efficiently, we have also developed a machine learning guided approach based on sequential learning Gaussian process. Time-resolved in situ synchrotron studies allow us to collect thousands of diffraction patterns during a flash time temperature sequence to rapidly explore the processing manifold. Next slide, please. In conclusion, energy efficient computing will require innovation in 3D integration and new materials and devices. Integrating devices into the back end of line is a promising approach to enable higher energy density, energy efficiency, and lower data latency. This results in thermal processing challenge for back end of line integration of materials, as the interconnects and dielectrics below the annealed devices must not be damaged. X-ray light sources offer transformative capabilities to advance future energy efficient microelectronic devices and computing platforms. Today, specifically, I've highlighted structural studies via grazing incidence X-ray diffraction of ultra-thin films for microelectronics, in situ photonic annealing tools that enable time-resolved studies of structural transformation and temperature changes within layered thin film structures, and finally, accelerated process exploration using machine learning guiding in situ process tools. And thank you for your attention.
Thank you, John. Appreciate that talk. And thanks to those of you who've entered some questions into the Q&A. As I said, we'll have time after our fourth and final talk to get to some of those questions, as many as we can in the time available. But we want to get to our fourth talk, which is entitled, Lensless 3D Imaging of Integrated Circuits. The speaker is Dr. Stefan Vogt from the Advanced Photon Source at Argonne National Lab. Over to you, Stefan.
Thank you very much, Andy, for the kind introduction. Next slide, please. I'll just pose the question, why do we actually want to image microelectronics? I think there's really many different reasons. I think most people on the call probably are interested for their own reasons. But fundamentally, you want to see both the structure as well as function of the devices across all of the relevant length scales. And that is something you need to develop new materials, new processes, many of these kind of things. Next slides, please. So if you want to image it, why use hard X-rays? We heard in the previous presentations quite a bit about X-rays in general. Hot X-rays, one of the things that's unique is they enable deep penetration. So without really damaging the sample dramatically, you can look very deep into material. On the top right-hand side of the image, you can see penetration depth of various X-ray energies. So if you use soft X-rays like 500 EV or so, you really look at a few hundred nanometers deep into, for example, silicon. As you go to higher and higher energies, like with 9 kV, you get about 90 microns deep. With 30 kV, you go through about 3 millimeters of material. So you can look at things that are not thinned or just a little bit thinned. In principle, you can achieve spatial resolutions that's only limited by the X-ray wavelength, which is much smaller than a nanometer. In reality, we're not quite there yet, though we're making, I think, quite a bit of progress. And in particular, you can achieve this both with the very high spatial resolution, but also simultaneously very large 3D field of view. In addition, you can collect comprehensive reciprocal space information. The previous talk showed a few examples of that. And you can also look at chemical information, including trace element sensitivity. On the bottom right-hand side, you can see tungsten vias in an integrated circuit spinning around, imaged by using X-ray fluorescence. In this presentation, I will primarily focus on just structural information. Next slide, please. So why use a synchrotron? Dava alluded to that very on. A synchrotron is really essentially a linear accelerator combined with a circular accelerator. In the case of the advanced photon source where I'm at, it's a ring that's really optimized for hard and high energy X-rays. So energies between say 10 and 100 keV or so. If you compare the brightness of these X-rays with a doctor's X-ray machine, you get this factor of 1 billion or so that Dava mentioned, and that enables you to do things that are just completely impossible to do otherwise. And of course, we've got an upgrade plan, such as other synchrotrons are planning, that gives us another factor of up to 500. Next slide, please. Just very briefly, what's the advanced photon source? Dava mentioned these instruments can be large. So you see on the right side an image of the APS. Its circumference is about 1.1 kilometers. We have 68 different X-ray beamlines where different experiments are carried out simultaneously. We are a user facility, so people come to our facility to make use of it, mostly free of charge. Though we have some proprietary experiments. We get in total about 6,000 experiments per year, and that leads to a fair number of publications. And these are across the various sciences, going from looking at integrated circuits to studying vaccines against COVID. Next slide, please. You're probably quite familiar with lens-based microscopy. On the left-hand side, it's a typical optical microscope where you can look at the sample. You can actually do sort of the same thing with X-rays that's shown on the right-hand side, where you have an X-ray source, you use a condenser to image the source into the object, and then you have an objective that images that onto a CCD camera. The problem is, in that case, your resolution is essentially limited by the objective, and those kind of optics are very difficult to make. So it's harder to go below 15 nanometers or so, and the efficiency is also quite low. There's other methods you can use. Next slide, please. And this is really sort of this tachography concept or lensless imaging. In reality, we're still using a lens, but it's not determining the spatial resolution. So what you can do is, instead of imaging the sample point by point, or in a single full field image, you're collecting a diffraction pattern. You see a typical example of such a diffraction pattern on the bottom right-hand side, and you can see the scattering from the sample going out fairly far. And then top left-hand side, through an iterative algorithm where you collect overlapping diffraction patterns, you reconstruct the actual sample. And in that case, you're limited only by how large your detector is in terms of what kind of resolution you can achieve and how stable you can keep your setup. On the top right-hand side, you can see an example, which is actually quite old now, of some early experiments we've done where the Stickson part of the image on the left side is sort of blurry. That's what you acquire directly with X-ray optics. And then on the same data set, using these tychographic reconstruction methods, you can actually zoom into far greater detail. So with that, next slide, please. This is some more recent data that we've applied to, I actually don't remember, an integrated circuit, maybe 16 nanometer process, I'm not certain, at 8.8 kV. And on the left-hand side, you can see sort of zooming into a field of view of a square millimeter. It goes through this again, it's a single image. The state acquisition time for that data set was about 3 hours. It's very compute intensive to do the reconstructions, but you can zoom into, as you can see here, lots of detail in that whole data set and preview later. Looking at this just in 2D is perhaps boring. And so if you collect many of these 2D projections, you can do a reconstruction, like tomography, and then look at the full 3D data set. Next slide, please. And hopefully the movie plays. This is a visualization of a 50 micron field of view of a 16 nanometer FinFET. Here we're currently metal layer 7 or so. That's the metal layer. You go through the vias, next metal layer, and again through vias, next metal layer. Again, metal layer through the vias. This is metal layer 1. And then you go through M0. And now, of course, since you've collected that data set, you can do, any sort of 3D virtual dissection as you want it and see it from the relevant angles. And of course, here you're just playing games. And then you can also zoom out much further to look at coarser structures. Again, the sample itself is not damaged, so you could image it again. Of course, X-rays do create a little bit of radiation damage, so I'm not sure it would work. Okay, next slide, please. Just a different visualization of the same kind of data. On the left-hand side, this is just a still 3D rendering, and on the right-hand side, it's just going stack by stack through a small area, 5 by 5 microns of the metal layers. Next slide, please. And here, because movies sometimes don't really play that well, I just pulled out a few of these cross sections. I should point out this is an older data set. We had a bit bleed through there. You can see that in particular in the via layers, which connect the metal layers. So there's bleed through from the layer below and above. But we have much nicer data since then, but weren't able to show it. Next slide, please. Just going down to more detail. Here you can see via 1, the M1 layer, and the via 0. And one more slide. And here you can see the bottom 3 layers. Next slide, please. So for us, those of you who know synchrotrons, the APS is currently down. Like Dava suggested or pointed out, we are doing an upgrade. We're ripping out the actual storage ring and replacing it with a brand new one that makes our X-ray beams about 500 times brighter. In terms of beam, what it does, you see a top right-hand side, essentially from a pancake type beam, it gets to a very small round beam. And for the kind of techniques that I was talking about today, this really improves either our data acquisition speed or sensitivity by this factor of 500. So it really makes a dramatic change. And you might wonder, how dramatic is a factor of 500 if you're already 1 billion times brighter than a lab source? If you look at the speed difference between when mankind started to fly and a space shuttle, that's a factor of 500 roughly. So it allows you to do new things you can't do otherwise. Next slide, please. As I mentioned, we've got an upgrade that's in process. It has about 815 million total project cost. and it improves our brightness by a factor of 500 and utilizes about $1.5 billion of existing equipment. On the top side, you can see some of the storage ring magnets that have already been assembled. And we actually got started on building a new beamline a while back. So the first one is operational, and we've built a new long beamline building that has two particularly exciting beamlines. Next slide, please. I should point out that one of the things that's also extremely helpful at the advanced photon source is that we are at Argonne. And so we also have a high performance computing center, as well as a supercomputer. And you can see here an image of Aurora. The kind of processing or data that I showed requires very significant processing. And right now, that's actually a bottleneck. Working with our colleagues across the campus at Argonne has already been very, very helpful, because we can use their skills and some of their hardware to really speed up that kind of analysis, and are very much looking forward to tie in more directly with some of the supercomputers down the road. Next slide, please. Dava mentioned that there's 5 light sources in the complex. I've listed them up here. I'm, as I mentioned, at the advanced photon source. They're all optimized for somewhat different experiments. So the advanced light source, for example, is really fantastic for soft X-rays. APS is optimized for hard X-rays. In general, all of these user facilities provide access to the resources via proposals. These are generally free of charge as long as there's intent to publish the work. And you get access to not just time on the instrument, but also support from the facility staff. There's also access modes for proprietary experiments that's best discussed in a bit more detail. In general, if you're interested in any of that, I would strongly suggest to reach out to those facilities and talk with some of the beamline scientists before you put in any proposals. Next slide, please. And with that, I'd like to thank everyone for taking the time and listening to this webinar, and also to all our staff that actually help make these kind of experiments happen, and our collaborators, without whom we couldn't do any of that work. Thank you.
Thank you, Stefan, and thanks to all 4 of our speakers. I know the audience is muted and can't actually applaud, but I'll applaud on their behalf for all 4 of you. So thanks for that. And if the 4 speakers could turn your video back on, we now have some time for the Q&A, and I will do my best to get through as many of the questions as we can that were asked. We probably won't get to all of them, and if we don't get to yours, those of you who asked, I certainly apologize. I'll encourage the speakers to give informative but hopefully concise answers to each, so that we can walk through that. And so I'm going to start with Patrick. We got a question about the costing for EUV tools and the challenge of designing the next. So the question is, do you see value in, and I think you're in a good position to answer this question, Patrick. Do you see value in DOE labs working together to develop the beyond EUV science? What would be the role of industry in developing BEUV, which I think means beyond EUV science and technology? And do you see non-lithography techniques taking over from the traditional quote unquote chiseling out materials?
All right, so for beyond EUV, I think what the speaker or the person asking about is the next wavelength. So there's been some discussion of going to 6.7 nanometer wavelength. For sure, the national labs have, that would be a great place to do this kind of research. It needs to happen early, right? We saw for EUV took 30 years. So if we're going to go this path, we should be working on it, and the labs are uniquely positioned to do that. The main question for beyond EUV is, will devices actually be able to benefit to scaling to trying to pattern features at less than 6 nanometer half period, as we can do with the current wavelength? So that's the major question, but these things take a really long time. So if there's any possibility at all, we should be exploring this front. When we started EUV, nobody believed it would ever happen, but yet it actually happened. So the other question, do you see non-lithography techniques? Well, that's That's been talked about for a very long time. I see a combination of non-lithography techniques with lithography techniques. So combining selective area deposition, selective area etch types of processes combined with some patterning process. Thinking about an entire lithography-free process, I think it's a little too constrained for the types of chips that we're talking about here, but there may be some devices where that could be feasible.
Great, thank you, Patrick. Appreciate that. Let's see. Let's take it's a question for maybe for Stefan. There was a question about for Stefan about, is it possible to, well, there are a couple of questions. One is your imaging technique able to detect a chip that wasn't built to spec, and might this help somebody tell if the contracted fab had not built it to spec or had modified the design? I guess it's really a question about sort of failure analysis, and is this an application of the technique?
I certainly think so.
Have people been doing in that, as far as you know, has that been implemented yet, or is that still too, or do you not know how?
I think, as I mentioned, there's a lot of interest in this, and we are collaborating with a number of people from different areas that are really pursuing this for their specific interest. So failure analysis is clearly one of the things that people want to know about.
Mm-hmm. Thank you. Okay, how about Jay? Can you elaborate a little bit on the Polybot, how it chooses synthesis recipes without interventions? For example, how big was the training sample set beforehand? How versatile is the method? Can it be used for things outside of the initial training set, or does the training set sort of set a boundary condition on what you can do with it?
Mm-hmm, mm-hmm. Yeah, sure. For example, like one of our research is to produce conductive polymer thin film, right? For that one, we basically pre-train the machine learning prediction model by very small data sets, like 10 data we generated from robot. Then we get a decent prediction model. Then we start to incorporate the machine learning prediction model with an optimization algorithm, like it's active learning. Then we use this combination to guide the robot to choose the future recipes in an iterative manner until reach our goal. So this training data set is pretty small. Then we generate a lot of data, right, during the exploration period. I think the method, if we are using similar processing method, for example, here we use row-to-row compatible slot die coding. If you are using similar solution processing method, the data sets should be suitable for your own outside training as well.
Thank you, Jay. Okay, John. Well, I think this is a pretty straightforward question, and that probably applies beyond John, but it was aimed at you, John. So, is there a way we can visit your grazing incidence X-ray diffraction experimental setup to see?
Yes, you can. Yeah, if you please reach out and contact me, and I can facilitate that. But sure, I can take you to see the equipment.
And I would say more broadly, others are welcome to weigh in. These are open access user facilities that all of these speakers work at. So they are built and operated by the Department of Energy or by the labs that are part of the Department of Energy complex as resources for the whole research community, both in the US and internationally. So they are designed to be open. And if you want more information about them, including the possibility of visiting, then I would encourage you to reach out to these facilities or these individuals to get that information.
Yeah, and Andy, if I can just follow up on that. I'd also like to reinforce what Stefan said. If you are interested in utilizing this tool for your own research, to please reach out to me and also the Beamline scientists before you submit a proposal. But we would be happy to work with you to try to maximize the science that you would get out of the tool.
Yeah, that's a great point, John, that I think is worth reiterating. And Stefan did say it, that this is true across all of our facilities. You're getting access to the hardware, but you're also getting access to the expertise of the people who work there, the Beamline scientists and the nanocenter researchers like Jay and others. So it's the combination of the two that really, I think, sets these facilities apart. Okay, there's a question sort of broadly to all the speakers, so I'll put it out there, and then Each of you, those of you who are interested can jump in. I think this is a question that's faced, where a lot of us are facing in research these days. What are the biggest data management challenges in your respective areas, and where do current solutions fall short? Where are you looking for advancement? Anybody want to take that first?
I'm going to give that one to Stefan because I think he's probably generating the most data.
He's got the most data.
It's a great question. I'd say, ask it again in about a year. So with the APS, due to the upgrade, we're expecting 100 times more data in about half a year or a year from now than previously. Right now, I would say some of the largest challenges are, one, just the large volumes of data that we are acquiring. So we expect 10 to 100 petabyte per year after the upgrade, and it's only going to ramp up with faster detectors and detectors with more pixels. So just storing it, dealing with it, and working with the user community to develop approaches where you can throw some of the data away. You use lossy compression. How do you share this kind of data? And then I would say, working with user communities on how we can work towards models where we routinely can use some of the DOE resources on the Oscar side in the compute space to help them analyze the data they collect, because few people will have the compute at home that allows them to interact with the kind of data we have. Not sure whether that answered it.
Yeah, that's a help. I'm curious, actually, it's not exactly the same question, but from Jay's perspective, what are you, obviously this autonomous process involves data and, the training data plus also the sharing of characterization data. How do you think about managing that data? Where do you see gaps in the data that you have or wish you had in order to improve these autonomous processes?
Yeah, Andy, that's a very good question. Actually, this is a question that we have been seeking for a solution for quite a while. So because now we are producing data, then how to classify this data, how to describe the data. I think now for example, my research field like polymer electronics is not just about chemical structure formulation. It's also including a lot of fabrication recipes, right? Processing conditions. Those are something it's very hard to capture. So that's why I think now we are working on with a lot of chemical engineers to see whether we can not just including polymer like chemical structure formulation, but also including processing parameters, morphological parameters into our database so that we can have a more complicated prediction model from the chemical formulation to the conditions that we process the material and all the way to the properties. This is something we are trying. I don't have a clear answer. I need time to give you the accurate answer, but yes, this is what we are working on.
Yeah, work in progress. Very, very exciting. Okay, we probably have time for, let's say, one or two more. So this is a question for Stefan, but I'll just ask it and see how you want to deal with this. So the question is it possible to analyze similar imaging data, I think like the movie you showed, when the circuit is in operation? It's a good question. I'm not sure the value of these sort of structural imaging during operation, but maybe I'm missing something. So I'm going to ask it and see where you want to go with that.
So I think that's a great question. I would say that it really depends on the spatial resolution you're trying to go after. If you're looking at the finest structures like I shown, where you can get down to, in one layer, in a real operation, I think that the dose on the sample is so high that it'll do something, but not what you intended to do. However, I can see for very simple circuits, it might work, or where if you stack chiplets, for example, and you're interested in how things change as the device heats up during operation, you may be able to just from externally change the temperature and do things like that, and then see in situ how does that work, how does that change the sample. So I think those will work, but real operation in terms of an Intel processor and hey, while it's running, let me see what changes. I don't think that will work.
Because you think the beam is going to interfere with the operation, or vice versa? I mean, was it?
Yes.
Yeah.
So the dose is very, very high. So you create tons of electron hole pairs that will, you know, that'll make changes. If you have very coarse, so there are some experiments that are looking at development of radiation hard microelectronics with much coarser structures. So there you can certainly look at, you know, trying to poke individual parts of a chip and see how does the system react. But if you want to image things in situ at the highest resolution, the doses just become really, really high.
Great, thank you, Stefan. Okay, I'm going to take maybe just one more, maybe two if we go quickly. We'll see. So this is a question targeted at, and it's a little beyond actually the talks that were given. So this is interesting to think beyond, but it's targeted at you, Stefan, but also at Jay. Could one of you comment on the potential applications of X-ray scattering and imaging in polymer-based electronics? In other words, the types of systems that Jay is working on, and how you might apply the imaging that you're doing, Stefan, to those polymer-based circuits. Is that possible? Do you see opportunities there, either one of you?
I mean, maybe I'll go first, and Jay then completes it. So right now we are actually doing on experiments we did experiments before we started the upgrade on some of these kind of devices. So yes, there's absolutely opportunities there. If you look at scattering, you can see some morphological changes, for example, really well. There's also opportunities for chemical imaging. The ALS is probably better suited for those kind of experiments. So it really depends on what exactly that you're after. Jay, maybe you have additional perspectives.
Yeah, I can add two more. Talking about self-driving lab, I also introduced like Polybot. Our ultimate goal is to integrate APS together with us, right? The kind of complementary expertise together. So actually, we are working together with X-ray scientist Joseph. I think he is also in the in this meeting. So we are trying to have an automated setup in the APS as well, so that we can mirror the property. The meantime, the X-ray can give us the information to understand why this material at this condition gave us this property. So this will give us a very good understanding in terms of polymer electronic development. So this is something ongoing as well.
Great. Well, thank you all. Thanks for that answer. And it is, I think, one of the things that I hope you took away from these talks, that while we only had 4 people here talking about their specific work at 4 specific facilities, as Dava noted in her introduction, we have many facilities, and each one of these facilities has a huge range of capabilities at it. So I encourage you, if you're not familiar with the facilities, to use the websites to reach out for more information in the area that you're working on. So I want to say my thanks now as we wrap up to all 4 of our speakers for taking the time today to speak with us, but also, of course, the time they took to prepare for this webinar. I hope that those of you who joined appreciated it and enjoyed it. I'm going to now ask if Adrian, you could put up the final slide. We've got a few more. This is part of an ongoing series of webinars that our Scientific User Facilities Division is organizing, and Dava is going to say a few words about the planned topics for upcoming webinars.
Hi, thank you, Andy. Yeah, so we are. This is part of an ongoing series. You know, we had our sort of first one, our kickoff one in January, and we intend to continue this with sort of focus webinars in different areas of, you know, national priorities. So upcoming webinars, we don't have dates or agendas yet, but we intend for clean energy, and this may be more than one, actually, like, you know, perhaps covering batteries and biofuels and other areas within clean energy, because that's a very broad topic. Also biopreparedness, drug discovery, other areas of how our facilities are contributing to being prepared for the next pandemic, for example, and also advanced manufacturing, decarbonizing manufacturing through studies of additive manufacturing, 3D printing, and alternative processes for making carbon-intensive materials like steel, for example. And as Andy mentioned, yes, we only have the way these webinars are formatted, we have 4 slots and we have 12 facilities, so we can't cover all of our facilities in one single webinar, but we will be covering, we'll have contributions from all of them over the course of this series. So please stay tuned. Look for those webinars, webinar announcements in the future. And I want to add my thanks to everyone. First of all, for everyone who came and watched. I hope it was informative and useful to you, and especially for our 4 speakers for sharing their expertise and their time and their work with us. Also to Andy for moderating, and our SC Comms team for helping organize this and publicizing it, and especially Adrian for managing the slides and all the logistics here. So with that, I thank you very much, and we'll see you next time.
Hi, everyone. Thank you.
Hi.